you a brief overview of what we are. Our goal is to focus primarily on spacecraft between the 1 to maybe 100 kilogram sized satellites. So not exclusively CubeSats, not exclusively microsats themselves. For us within AFRL, it's dominantly focused on what we're calling the tactical layer. So how do we help the disadvantaged warfighter in the field? And a large part of that, and where this thrust of research using the Globalstar network comes from, is how do we use path-agnostic communications? So if you have access to an IP address, you fundamentally have access to your comm data. Is the impetus for all of this with the mission sets that have flown. So moving on, I want to start with the Simplex first and kind of the use case that we see with it. Jumping on to slide 3, effectively it's a unidirectional downlink of small messages. You can do integer multiples of 9-byte packets. What's been tested on orbit is using 36-byte packets. The modem, though, is capable of going up to 144 bytes. The value-added reseller that we've been working with has only implemented the 36-byte messages, although it's something that in the future we would like to explore going up to higher message formats. And I'll kind of discuss the reasoning there in a moment. The flights that we are aware it's been on, Taylor University did their TSAT mission. It was launched in 2014, and it was a secondary on a SpaceX Falcon 9 on the second stage itself. So it was an extremely low orbit. I think it was only stable for about 40 days. So extremely low altitude in that particular case. Geographic coverage wise, not too bad, but not a lot of time domain associated with it. Then we sponsored Gears 1 and Gears 2. One of them went off of the ISS, and the other one went off of the aft bulkhead carrier on the Avspace 5 launch. And then most recently, starting in May, we have our SHARC satellite, which was deployed off of the ISS as well. And then hopefully in the future, we basically baselined this modem from its practical use case standpoint on all of our future spacecraft. The utility for this modem is definitely there, and it's one of the things I really want to highlight. I should mention everything that has flown thus far is the STX2 modem. The STX2 is now, it's in obsolescence, and the STX3 is coming online, and I believe there's a demonstration mission of the modem flying on orbit here in the next 6 months off of ISS, I want to say. So from a heritage standpoint, we're talking about a modem hardware itself that is on its way out, but fundamentally the same protocol, same use case with the follow-on product line that's going to be demonstrated here shortly. On slide 4, I've got a coverage map of both Gears 1 and Gears 2. This is technically all data from Gears 2 itself, the Avspace 5 mission. The orbit parameters are there, so it's a pretty diverse altitude from 360 to 700 and at 55 degrees inclination, so it's still under the inclination of the constellation itself. The only mission that was anticipated to go to a higher one thus far was U2U, and that has as yet not flown. Here we're looking at 36-byte messages, and there's about 21,000 Simplex beacons plotted globally. And so you can see there's a little bit of, it's a little bit more sparse, I guess, in the Pacific Ocean, and it's fundamentally based off of how I understand the Globalstar network operates as a bent pipe. So you have to have line of sight to a Globalstar constellation satellite, and then that has to have line of sight to one of the ground terminals. So still, though, quite fantastic coverage. And the use case for us in this particular case is kind of like a black box data recorder. You can get low-level telemetry, voltages, currents, power, charge of your batteries, those sorts of things, nearly globally distributed. The interesting facet of that and how it plays into our mission set is here, from an economic personnel manning standpoint, we're fundamentally able to know how the satellite is behaving while it's over the horizon. So the focus of line of sight passes, and I apologize, I walked in when Marcus was discussing Iridium, where there's still a use case for line of sight radios. We still fundamentally agree with that point. It's now with this kind of a modem where I know how the satellite engineering side is doing, I can focus the entirety of my line of sight pass on mission data, whether that be downlink past experiment data or being able to confidently schedule out the next set of experiments. That's the real end state goal with the modem as we see it. We also have the SHARC satellite. So I push my keyboard. Sorry, we have the SHARC coverage map. This one's a little bit different. We discovered once we were on orbit that we were using the lowest frequency channel, 1611.25 megahertz. We've had about 30,000 beacons go out as of the time that this data product was produced. The interesting thing about 1611 is it's only able to be received through the ground stations that are in North America. So this kind of gives a distribution associated with the North American continent, which is still fairly wide. What we're seeing right now, and it still fits the use case to a certain extent, is we can get contact with the satellite, see how the temperature's doing, see how power's doing, about 15 minutes out from a pass. We have ground stations in Florida, Texas, and New Mexico, and Hawaii. And so we're able to still see how the satellite's doing and focus predominantly on mission data. Travis Willett, who's joining me, has been running flight ops for the past several weeks, and well, he's had the lion's share of all the problems recently, which is great. I got to be on vacation. And part of our discussion has really been centered around this is really all the data we need from the avionics side coming down over beacons. And now we're able to focus more exclusively with line of sight on our GPS payload, our C-band radar transponder, which is part of that spacecraft's mission, which is really cool. It fits the use case. It's not quite global, but it's nice to know that it still exists. More importantly, though, the density that you see the packets coming in is quite uniform over the area that is closest to the U.S. continent. So kind of going back and forth between GEARS and SHARC data, there's not a giant disparity between how many beacons you get in a given unit area of latitude and longitude, which is nice. And the other neat thing that we're also seeing, and we saw this with GEARS, both GEARS payloads as well, was you're getting beacons in sequence. About 80% of the time, you're getting all of your beacons delivered with their unique identifier, just message set 1 through 9, for instance, and not dropping individual ones as a dominant case, which is really cool, because then while 36 bytes is not a lot, I guess I shouldn't have jumped into that. While 36 bytes is not a lot, we can break up the content of the messages. So one might be dominantly thermal data, one might be dominantly power data, one might be dominantly attitude data, all off on the side. And so we can rebuild that entire snapshot of the spacecraft fairly easily without dropping too many packets that are valuable information. Sorry, let me go on. On slide 6, we have the power profile. What's really nice about the STX2, and I presume about the STX3, although we haven't benchlined it,
just so you know, the STX3 is the same as the STX2,
Perfect.
Just a lot smaller, lower power, and it has an additional set of AT commands and
Gotcha.
other features, but otherwise it's the same.
Oh, perfect. Okay, so
Same transmit power, everything.
Oh, that's excellent. Okay.
But it is the same RF power though.
Yeah.
Okay.
Yeah, same RF power.
So it's just basically more efficient transmitter. So
That's right.
Okay.
So thinking back to what that chip was, and there was a quarter next to it, the STX3 is the size of the quarter.
Gotcha. Okay. And it looks like the pulse goes about 1.8 watts.
Yeah, so this is measuring DC draw in,
Okay.
and what's really nice, so the Simplex modem is very deterministic, and from our standpoint, to go to operational CubeSats, one of the main focuses has to be for us on robustness, and determinism is a large forcing function associated with that. Since the Simplex is entirely controlled by the spacecraft, you pass a data, it will beacon out, versus the handshake protocol necessary for the duplex modem, and I also presume the Iridium modem, you lose a little bit of determinism with it. This is nice from the standpoint of when I pass at 36 bytes, I know what the power profile is going to be exactly like. And since it is globally distributed, I can really model that well. For us, what we're trying to do is identify with small sats the fact that we know that every one that we're going to fly will have a case in time where it is going to tumble. And making sure that you're power positive in that particular use case is rather difficult. And so the Simplex provides you a lot of peace of mind with not a huge additional swap burden to get that data and understand how the spacecraft is doing once you do go into the tumble state. Also with this, it gives a nice time series of what an entire message set looks like. So from the time that it is, the CTS line in red goes low and you can pass data across, which is that short green burst, there's a short processing period, and then the actual transmission of 9-byte packets. All said and done, an entire beacon message set I think just takes, is it 1.3 milliwatt hours? Yeah, so a very, very low amount of power that you can beacon out, and you can do one every 8.1 seconds. So call it 10 seconds, you're pretty good. You can do 6 of these message sets in a minute, which is a huge benefit. And so we're beaconing right now on SHARC at roughly once every minute during the very, very early contact phase. And that was where the lion's share of our data was coming from, even when it was only being received over the North American continent. And after that, we've now dropped it to once every 5 minutes and are trying to schedule it just around the North American continent, so we're not wasting power dominantly. One. So then from our standpoint, I've kind of hinted at the intended CONOP. So I mentioned we have that 80% of packets are delivered in sequence. So for us, what we do, because 36 bytes isn't a ton, we break it up where we do have one beacon set that's thermal, one that's power, one that's attitude, position, and kind of work your way through the entire avionics telemetry set of what you find valuable. And so we define those as distinctly different messages, but we build them up as a message set. So in our case, SHARC has 9 different beacon types, and they're generated all at the same time. So if you get beacon 1 through 9, the beacon timestamp associated with 1 is what is actually a timestamp for all 9. So you don't have to waste putting a time variable in each particular message. And then we can build that full snapshot of the vehicle. And so that's what we were using as that big piece of initial checkout, because we can build long time domains without any extra effort associated with downlinking data over CONUS. So that was really, really helpful. We also, so in terms of areas to explore where we would like to go is looking at different beacon message sizes. So kind of coupling that with the STX3 coming online, from the user's manual with the modem itself, it can go up to 144 bytes. That has a particularly interesting use case from the standpoint of, if you think about a GPS message of best XYZ from like the colloquial Novotel product family, 36 bytes is not really enough. You can have time, you can have position, and you can have velocity, and generally speaking, you're going to have to make a break across that family at some point. Now, 80% of them coming together, so you can have time in one beacon, worst case scenario, position in a separate, and worse yet, velocity in a third. You can still build that back together as this is my ephemeris, but what would be nice is a 144 byte packet, or like you're talking about with the Iridium modem at 300, you can put a real Novotel best XYZ message all together with the 1 sigma error bars, which is particularly powerful in a message set like that. So that's an area we'd like to kind of provide a bit of a forcing function to explore. Also, at 36 bytes, what we've had to do thus far, and this is more of a mandate from our organization, we have to put some level of software encryption on it. Generally speaking, we don't pass mission data down because that has to go to type 1 encryption. And so what we've been able to get away with is avionics telemetries at FOUOM class, and so we can get away with, say, OpenSSL running on the flight computer and passing 36 bytes. However, at 36 bytes, you're only talking about 2 cipher blocks, and so we're not able to do a full encryption at CBC with an initialization vector. And that's kind of a problem. And that begets part of the, if we can go to 144 bytes, we can do a little bit of a tougher encryption scheme in the long run. Right.
That's sort of the baseline. You need at least 144 bytes to get 2 encryption blocks plus some usable.
No. So the encryption, each cipher block is 16 bytes. So as long as you're an integer multiple of that, what we've had to do right now is at 16 bytes, 32 bytes are encrypted on electronic codebook style of encryption. And then we have a header that's in the clear, which is more of a beacon count, things that are of no consequence, that it's in the public domain. Again, that is a forcing function of AFR, of the Air Force itself. What we would like to do, and this is purely just a like, if I can have an initialization vector and not sacrifice too much of the payload data of the message set to that, I can do CBC, and then everybody kind of sleeps a little easier at night. Whether that fear is founded that I really need to have CBC style encryption is a whole different risk space that is a lot of fun to argue with the cyber folks about.
But I think we're all being driven that way.
Yeah.
So, we may as well just suck it up and
Right.
go for it.
Right. So it would be really interesting to fly a mission. And I can see where, from the standpoint of smaller beacon set, knowing that it takes 8 seconds to send the 36 bytes, we're talking about a substantial distance being crossed. So the chances of dropping packets goes up significantly when you go to 144 bytes, because now you're talking about 4 times larger. So you have realistically, what, a minute-long beacon message is where you would be in the rough neighborhood of. That's not great. So there's room to play, and we'd love to do a demonstration mission here in the future where we can explore different message sizes and how effectively they come down going forward, purely to solve the problem. Can I get all of my GPS information in one packet? That would be nice, right?
It really would. And it'd be nice to have it kind of settable per packet. The
That's fair,
36
too.
byte thing we're working with is just set in firmware with the radio as we receive it. So we constrain all of our data to fit within that 36 bytes. And that, will involve some bit level packing of, our ephemeris packet will also have the command count in it because we had a few extra bits in there that we could put that in. If that were variable, then we can have really small packets that we're beaconing out all the time that have really, really critical data, and then some larger ones that may come down every 10 minutes, 15 minutes, 20 minutes with ephemeris or a payload or some other such thing. So it'd be something nice to play with in software rather than cramming everything into a 36 byte.
We're also looking at, Travis kind of hit on it, decreasing the byte resolution. Right now, for instance, we're passing down telemetry data associated with our thermal sensors at 16-bit resolution. We don't really need to be. We could do eighth of a degree resolution at 8 bytes. I mean, that's more just a packing thing for our own, or 8 bits, sorry, for our own edification, so we can pack more efficiently. We just didn't get around to it on SHARC, but the use case is there. U2U, which I didn't really hit on, is one of the first missions that we were exploring of actually passing down mission data over the Globalstar Simplex. So this guy was a 2U satellite, it had an electron spectrometer, so it was fundamentally just looking at total particle counts over an energy domain. And that was going to be beaconed down. It ultimately didn't fly, or hasn't flown yet, one of the two, depending on who you want to ask. And that was actually a really interesting use case as a weather sonde, if you will, of what the high energy particle environment is doing. And what was cool about that is you don't need any capital asset investment on the ground to move a substantial amount of data to the ground just forever and always. So
same kind of data all over and over and over.
And yeah, in that case, it was the exact same. You're absolutely right. We had a few other packet types, and there's a gyro. So we passed a little bit of a time domain of the gyro to see how we were tumbling. But to your point, Bruce, exactly right. We could just pass the exact same data down over and over and over again. And so that works out really well. SHARC is a C-band radar transponder mission. And so we have to pass down, I think, 12 hours worth of GPS data before and after a radar calibration over the United States. You're not doing that over Simplex. There are certain use cases, but I think what's really cool is the space weather side. U2U makes a very compelling argument that you can pass the mission data down over a Simplex modem like that. So I think the case expands beyond just the mission data. The dominant case, I didn't want to be hyper focused on it, has been avionics for us, but I think it can go places.
We'd be interested in exploring what instruments you're flying. That'd be a really cool thing to do jointly if that's appropriate thing to do.
Yeah, absolutely. I think that would be great because we get folks from our sensors directorate, RVB, the Space Weather Battalion, or Space Environment Battalion, coming up to us asking if we can fly sensors for them, and the answer is not always yes because we're busy. But if you have bandwidth.
We might on our 6U. So
okay.
If we have some space, so I'd really like to do that. Maybe that'd be possible collaboration over several different threads. I think kind of cool.
Absolutely, yeah. So I should mention with the Simplex and the Duplex alike, we've been working with Near Space Launch as the value-added reseller for working with these modems. So the protocol they've implemented in terms of talking with the modem or over the the actual RF link with the network has been implemented by them, and so their use case or their demonstration is much more valuable there. Ours is more at the system level in terms of how the modems have behaved on orbit. And that's particularly interesting with the duplex. So this modem has two operational scenarios that it can be used in. One is an SMS, and we call it kind of our command uplink. It's a small message format again. In this case, because it's ASCII 85, you really only have 32 bytes available to you, so not much more than a command count and an opcode, and maybe a time to execute at is all you can really get away with in it. But that's still extremely powerful when you know you can send it anywhere. Also associated with that, they have the data calls, which allow for more of a streaming at a unburdened rate of 9.6 kilobit. I think it works out to 900 bytes a second when a data call is initiated. And so we've flown this on Gears 1 and Gears 2. SHARC has it, and then I'm familiar with Raven flying it. I don't know, only limited context to how it behaved on orbit. The first three are ones that we were deeply involved with, excuse me. Kind of divorcing the SMS functionality from the data call functionality on the modem. We're still assessing what the value function is for the swap investment on the spacecraft for flying the modem. What's really exciting, and I'll get to this on the future slides, we've shown that you can get SMS over the globe. Unfortunately, there's a time delay associated with it and a little bit of non-determinism of how long it'll take to get the SMS there. So it's not so much I see the spacecraft from, say, Simplex data is going into a bad state and I need to put it in safe mode and it'll immediately get there. That's not necessarily the case you can count on. It'd be more of I need to schedule out a radar calibration 2 days from now. Then you're fairly safely going to be able to execute that sort of exercise in terms of, say, SHARC here with an SMS. Data calls to that end also fit in that category. There is a time domain associated with how long it takes to move the data to the ground. I should caveat with both statements of that associated with how how the modem operates. We have not specifically oriented the antenna zenith facing or tried to track a Globalstar satellite itself. When we've been using this, it's either been in our survival mode on SHARC, where the spacecraft has been, air quotes, tumbling. It was at less than 0.2 degrees a second, so fairly slow. Gears 1 and Gears 2, well, particularly Gears 2 coming off of the aft bulkhead carrier was spinning at 4 RPM. That was a non-starter. We got SMSs in and no data calls. But SHARC, on the other hand, we were able to get data calls and we're able to get SMS, but it's been a very limited data set. And with how the vehicle was behaving and the lighting scenario it was in for total illumination time on orbit, we've had to turn off the duplex for a period of time while we've been checking out the rest of the vehicle, and then we're going to come back around to that experiment. So all I have to say on the duplex is, hey, it works. You can get SMSs and you can do data calls, but to what global extent? It's a limited data set. Each one of those blue dots is where we got an SMS in. So there's about, what would you say, 30?
Yeah.
We sent about 30 SMSs to the satellite of no-op commands. We were fortunate, again, this comes back to the lighting scenario. When we were ejected, we were going into full sun. We were unfortunate because when we got ejected, we were going into full sun. So that power scenario worked out really well, but the thermal scenario didn't. So we had to turn off the duplex while we were in full sun about a week and a half into the mission because the system was overheating. And that brought us right back down into operational temps. And we have not turned it back on yet while we've been checking out the other vehicle systems. This zeroth order, where you're seeing SMSs coming in, shows that the SMS capability is there. And that was also demonstrated with Gears 1 and Gears 2. The latency that we've seen, with SMSs is about 4 to 14 hours. So again, that comes back to but again, this was a tumbling spacecraft. It didn't have full latitude control. I cannot confidently say the antenna was up. With the amount of tumble, with the body rates that the vehicle had, it'd be reasonable to say, yes, the antenna is likely oriented up for a substantial amount of the orbit, but then oriented nadir for a substantial amount as well. So in that particular case, it's kind of hard to say if this is indicative of the modem or indicative of our attitude state. I would lean more in the camp of indicative of our attitude state.
Yeah, that's an important variable to understand. Is
Yeah. So
It's going to be due to the to your attitude
Yeah.
state, and because the if you have a modem that's in service, I mean, it's sitting out here in
Yep.
Ames or whatever, and you send an SMS, it'll get there in a few
right,
seconds.
and that's the experience we've always
and,
had on
and
the
definitely
ground.
you can do that. But if you have the thing powered off and you send the message, well, it can't deliver it, so it puts it into a queue,
Right.
and then it does a retry schedule. And so when you look at that and say, oh well, it does it every a try for every 10 minutes for the next hour, and
Yep.
then it gets it stretches it out. Well, then you get into these others where between the time that you have service over the different places, and
You might not
and
actually
where
have a
the
message. Yep,
where
that
it's
makes
like, oh,
sense.
he's alive, and I'll send the SMS to him.
Totally makes sense.
That's how it all happens.
So our experimental goal with SHARC is to go back and both do a sun pointing test where we optimize the antenna axis zenith, which from our experience so far, that body axis has been oriented within 30 degrees of zenith itself when we're sun tracking. And then we'll also go through an experiment series, which is net power negative, so we can't do it for a terribly long time, but orienting the antenna zenith for about 2 days, and then go back into a sun pointing state just because the batteries would discharge on the vehicle. And so that'll give us a better, more deterministic test of, okay, we're giving this the best attitude state we can. And like you're saying, if we're out of a service region or if we're in a service region, how long does it take for the SMS or data call to be initiated? So that's an experimental goal that we're hopefully going to get back to within, I guess, a couple weeks. Now that we're most of the way through initial checkout. So that's really exciting. The data call coverage is by far the most exciting thing that we've had on the mission yet. We deployed off at the space station and then decided to go get a celebratory beer before it came over CONUS to start line of sight passes. And suddenly we get back and there's data coming down. And we were shocked because the duplex was initially on. So we really wanted to go get another celebratory beer, but there was a pass coming up and we couldn't. So as we were able to experiment with this before, the thermal scenario put us in a state where the satellite couldn't handle the additional heat load of the modem being on. And that was it was the easy kill to get the thermal bounds back into operational limits, unfortunately. What we were able to do is the ideal path agnostic use case. We shoved avionics telemetry into the duplex queue. And I should mention, the duplex queue itself is a function of what the value-added reseller has brought to the table. They have a small Linux microprocessor that's running rsync on board. So you push files over, and when there is a service connection, the queue will be dumped to the ground and then passed on to you as the end user. So what we were able to do is just send a command to push 8 hours worth of power data, because at the time, in the first 7 to 10 days, power was by far the thing we wanted to know the best. We pushed 8 hours of power data into the queue, and about 8 to 14 hours is how long it took for the data to come down. And in sum total, I think we moved about 500 kilobytes without a ground station, without really much user input besides one command that went in. And actually we sent it up over SMS as well as the data call uplink, which is kind of cool in and of its own right. So entirely moving data without a ground station. That's the dream, is that we can get there. With the experiment series that we want to do with SHARC, where we orient the system as close to, or the antenna as close to zenith as possible, we'll explore that more. How do you use the SMS capability to get commands down, or get files down, excuse me, as well as how do you use the data call service on the uplink side to move files over. And then we'll still always have our backhaul of line of sight data to get the performance off of the duplex, how many service connections it's getting, what the RSSI is across the globe as we're able to build that up. So that's a really exciting piece. We're all shocked because Raven, I believe, flew on Worldview 4, and their operational use case was to only have the data call functionality, and I don't believe that they saw data calls. I do believe that they were able to send SMSs. The vehicle was not configured to accept SMSs as a command set, but it showed that the modem was there, it was online, it was getting connections, similar to kind of the graph that you saw associated with SHARC, but it was the data call side. So we were a little wary if this would work, but it really does look like it will. So now as we can perform more deterministic tests of what do we have to do to help facilitate data calls down to the ground. That'll help us make a better assessment of the swap impact for the vehicle and the value return that it has on the system as a whole.
Was Raven stabilized? They were pointing their antennas.
That's the other part that I don't know, is if they were specifically trying to point the antennas in it. They were also in a very near polar orbit going off of Worldview 4, which could be another compounding factor. Because I think, Marcus, when you and I have talked in the past, range rate has been an issue with Iridium. I don't know, Joe, if that happens to be the case with your guys' experience associated with Globalstar. If you do have the Globalstar satellites that they're 60 degrees inclination, correct? The constellation.
Constellation's 52 degrees.
52,
inclined.
okay.
Yeah.
If being at polar, if you have a drop off because you would have sustained a substantially higher range rate, if that has a significant impact at all. So that's something that we also want to try and make an assessment of with SHARC as best we can. So the potential, as that first bullet states, is here for persistent contact with the vehicle and ideally responsive commanding globally. So if we can get to the point where data calls are a little bit more uniformly distributed, even if that happens to be more closely locked to landmass, it's still a substantial amount of the time that's not currently available to you on orbit. So there is a huge economic manning savings associated with being able to just access the vehicle when it's over landmass. Fundamentally, dim light operations of 8 to 5 becomes a possibility as opposed to tracking your day with the line of sight contacts wherever the ground stations might be accessible at. For SHARC, what we've demonstrated is about 500 kilobytes, and that was within the first 10 days once we had to turn it off. So there's a huge potential here that we want to explore more. We want to work with the Blue Canyon guys, Near Space Launch, and you, Joe, as well, to understand what the fundamental differences might be associated with SHARC and Raven. As I understand it, there's messages being sent back and forth with the duplex to the constellation that I think you guys see. Mm-hmm. And it'd be great to understand what might be fundamentally different associated with the SHARC connections versus the Raven connections as we move forward, because understanding that and being able to say where the constraints are that a good connection can be established would be a huge boon. And then
I don't think that the Raven issue had to do, the Raven issue didn't have to do with the constellation or the modem, the hardware or anything. Whether it was an integration issue or whether it was the programming of the modem, which frequencies it was programmed for, there may have been something else going, but the fact that Raven just wasn't getting anything other than these sporadic connections was just really out of sorts with what you guys have done, the Russians did, other people. So I mean, we know that it works a lot better in space than the nothing that Raven got.
Yeah, that makes sense.
There was just 100%. Something,
Yeah, that makes total sense. I'm with you.
So Kyle, do you guys know the attitude of SHARC?
We do, yeah.
Because it should be flying like this, right?
So dominantly,
it should be the maximum drag position about the CG.
No, so we our C-band radar transponder is on the long axis. We're a 6U long spacecraft. Right. And so we would actually fly minimum drag to the ground to facilitate that. Our standby state is actually to track one of our largest body-mounted solar panels, say, towards the sun. And then because we're using the Blue Canyon attitude system, we're able to optimize the antenna axis to point zenith.
And it is a patch, so you have a patch pointed towards zenith.
Correct, Yep, you got it.
And then if I could ask, or you can shoot me off and talk about the end, but the duplex is it won't fit into a 10 by 10 centimeter. It's long.
No, it's about 80 by 120 millimeters.
Okay, so you've got to fit it. You have to fit it longitudinally into.
Correct. Okay. Yeah. So the way SHARC was built up, I didn't really get into the specifics of the system. We had a monolithic structure. It was just extruded aluminum tube and then plates that avionics sub-assemblies mounted to. From thermal standpoint, that was really nice because you had a very direct thermal path of the vehicle subcomponents into the spacecraft structure. And that also helped facilitate how we would mount the Globalstar Duplex modem because it is that kind of odd form factor where it is long. So we're not talking about the traditional rail design. anymore with SHARC, and that made it easier, I would say.
Sure.
Travis actually had to put it together. I was on a sabbatical. So that actually is another area we'd like to explore that I didn't write down. So we currently have a SIBR topic open, and Joe, this might be of interest to you, where it's essentially it's art of the possible. What can we do with small satellite communications, power, et cetera, to help facilitate? In this case, path agnostic comms is one of the main called out objectives. If there is any interest in working on the Globalstar Duplex modem to change the form factor where it potentially is more amenable to a small sat, at least the 10 by 10 small sat form factor.
That's a big deal, actually.
You're right. I should have. I didn't think when I wrote that one down.
No, but
Thank you for pointing it out.
solvable.
Yeah, solvable. You're absolutely right. And then frequency authorization was one of the things.
Oh, excuse me.
So, is this the PDF version? I think it is. This will be fun. There we go. Hey, it is animated. Yeah. I'm not going to say that dealing with the frequency people has ever put me in the hospital before, but it might have.
So, Kyle, you now were commiserating, as we're trying to go through the NTIA process.
Oh, yeah.
About a year ago, it was frustrating, to say the least.
Okay, so as I understand it, and Joe, I'm so happy you're here because I don't want to say this wrong, and this is what I've been telling my management, so it'd be really good if I have to, it'd be really great if I have to correct myself. So both Iridium and Globalstar, as I understand it, they're sitting in the L-band spectrum, and they're authorized, the L-band spectrum is allocated as space to ground or ground to space, and that is what their authorizations are. What's nice, and the potential is there, the FCC experimental license process allows for you guys to file essentially a waiver to enable space-to-space communications, and that would be going through the FCC OET office. Love those guys.
Actually, they're pretty good until they were directed to divert us a little bit, right?
Yeah, and so we've actually been reading the experimental license a lot more, and some of the things that we've run into where they want to be the arbiters of the space resource, if you will, or the experimental licenses being cracked down for exclusively experiments associated with radio spectrum or actually outside the charter. To what degree you want to stoke that fire is up to you. So that's something we've been reading into. So the compounding problem and the rock and the hard place is fundamentally acknowledging that the L-band spectrum that both of these networks sit in is not meant for space-to-space communications is the first hurdle, and that necessitates the FCC and the NTIA working together.
Right.
And so from the NTIA side, maybe, the government side, when we have to go to NTIA, the way they view it, the way essentially the form is intended to be filled out is you're getting a specific frequency coordinated for yourself. And so when you say you're flying one of these modems, they view it as you're taking the commercial spectrum, which is a challenge. And so we participated in the 762nd, I don't know why they keep counting at that point, just put a date on it, SPS meeting, where the outcome of that is there was a call sent out by the SPS chair for how do we handle RDT&E satellites in the future. And what we responded with as AFRL was particularly associated with using commercial comms, which Air Force Space Command has their space enterprise vision. And part of that, one of the major tenets is having resiliency. And one of the logical conclusions you can draw from that is don't be reliant entirely on government satellite comms networks. Use commercial, like Globalstar, Iridium, Viasat, Intelsat, Eutelsat. Use them because you become more resilient by doing it. What we recommended, because all of those that I just mentioned would have the same problem, it'll be their license and their band allocation will not allow space to space. They're fundamentally not set up that way, is that RDT&E satellites would be delegated even at the government level to the FCC experimental license process. The rules as they exist are logically defined. They are for experimental missions, not just the frequency spectrum you want to use as an experimentation unto itself. And it enables the waiver process that I know Joe, you've participated quite significantly with us on with these past satellites, so that the commercial SATCOM provider can also file for the waiver at the same time, and then you don't have one entity and a second entity trying to talk to each other. So hopefully that works. One of the key parts of this, though, is the experimental licenses, as called out, do not enable operational assets. So for us in the Air Force, for you guys with NASA, there's that gets into some murky water. I mean, I guess from my perspective, just because it's what we know, the operational use case is very rigidly defined. So that's a hill that would have to get taken at a later date, but it would at least allow our experimentation now for demonstrating and building the bow shock that would allow for transitioning this onto larger vehicles and getting that resilient nature through multiple comm networks.
Hey, Kyle, Scott.
Yeah.
Hey, a couple of maybe points and questions. I think the question, the point you brought up about the FCC and the NTIA with the challenges from the government side trying to use FCC spectrum, I think it cuts both ways as well. So, it's also looking at the non-government side trying to use S-band and X-band, spectrum for a small set. So I think, the U.S. having a split spectrum system, which I think is unique from any other country in the world between government and non-government, creates challenges that we're all dealing with. Another interesting challenge is the ITU does not recognize experimental licenses. So even though the FCC is pushing us through the experimental license process, the ITU, and I had a conversation with Attila Mattis about this last spring, sort of indicating that experimental licenses are something that are domestic and the ITU doesn't recognize them. So I don't know where the ITU is going, but that's also something I think we need to think internally about, that these missions don't fit under the Part 5 Code of Federal Regulations for commercial satellites, or sorry, the Part 25. Part 5 works, but there's nothing in between that sort of meets our needs. And then just one other follow-up on Raven with regards to to our filing. We did our filing a couple years ago, and we just got a letter from the International Bureau maybe 3 weeks ago with input from Indonesia and UAE that they have concerns over the use of L-band spectrum that we're using. And I know that both the Simplex, or the L-band spectrum that we're using for both Iridium and Globalstar, is just above the ITU allocated radio astronomy bands, and so I'm not sure what the concern is, but we're gonna go down that road with the FCC to get their input.
Oh, that's really interesting. I didn't realize that. Okay. Huh.
Yeah, so I mean, we filed our API with the ITU, and then we filed whatever the one comes after the API. I forgot, notification, I guess. And then based on that, like I said, we got feedback letters from Indonesia and UAE with, I guess I don't know the correct terminology. I think it was request for coordination is how it was put at this stage. We're going to be going down that path and at least learning something from it, and be happy to, would love to coordinate and collaborate with Joe and the Globalstar folks to make sure we're using the correct vernacular in our response.
Okay, yeah, I have a section on talking about the frequency authorizations and the issues there. And Scott brings up, I assume it's Scott, it's just a
Yeah, Joe, Scott.
Yeah, a basic issue, which is that what we're dealing with, the reason you have to go through the FCC is that they are the representative to the ITU for the U.S. Registered constellations, for both of our constellations. And so the FCC, so that, and the ITU allocation, which was agreed at the work conference, that covered just the space to Earth and Earth to space allocations. Now the radio astronomy is another deal, because wherever we operate, when we're on the ground, when we're on Earth, we need to respect those, make sure that we're protecting the radio astronomy site. So that same requirement, that's not a new requirement. that's something we do just as a part of operating our system. So whether something's in space or down on Earth, I'll talk about that too, about how we have to, especially program the modems so that, we make sure that that's all taken care of, even when something is flying as fast as a satellite.
Yeah.
And so, there are a lot of different issues that need to be taken care of, and that's why we have to look at all of that. But I appreciate getting that, copy of that correspondence from UAE and